So now stable versus unstable equilibrium. So first off, equilibrium would have the total force is 0, acceleration, therefore acceleration must be 0, therefore the change in velocity must be 0. I'm going to define I hat, j hat as such, and I'm imagining a ditch that's shaped like a perfect parabola, and the bottom of the ditch is 0, 0, is where my x and y axes cross. I know u is equal to mgh, where h is the height above 0, so I'm just going to make the height is equal to 0, some distance h sub naught below the bottom of the ditch. And so mg is equal to y plus ho. So the distance from my x-axis to some point on there is y. If I distribute this, I know that y is parabolic in nature, crossing at my origin. And so I have mg ax squared plus mg h sub o. So just basically substituting in for y. This is a stable equilibrium because if I put a ball there and I gave it a little knock, that ball is going to come right back towards the center. So a stable equilibrium is that if you knock it out of place, it will want to move back towards where equilibrium is. I know du dx is equal to my force, so that would be 2 mg ax. And remember that I had that plus a constant. So I have mg times some height here, which I'm labeling as y, plus a constant. I talked about a constant in other videos. I take the derivative of mg ax squared plus mg ho. This whole thing here is a constant, so that's going to drop out, and I'm going to be left with 2 mg ax, as mentioned just now. I know that the total force is equal to 0 because I'm looking for an equilibrium spot, so I set this equal to 0, the I hat properly, and this only occurs when x is equal to 0, so that is where we would expect. That's the bottom of the ditch. To find out if it's stable or not, I take a second derivative. I get 2 mga. All of these are positive numbers. I know a is positive because the parabola is upwards, and so a has to be positive. So therefore, this is always greater than 0. Therefore, we're at a local minimum. Therefore, it's stable. If you recall, second derivative, positive second derivatives means that we're dealing with minimums, and negative second derivatives will be dealing with a maximum. We took a situation that clearly was a stable equilibrium and showed that the second derivative is positive, so it matches what we've done in math. So now let's take the other direction. Imagine that I have a hill here, which would clearly be an unstable equilibrium. I could have the ball right here on top. If I gave it a little knock, that thing is not coming back to the center. It is going to keep rolling. So that's an unstable equilibrium. Let's make sure that the math works out. Again, u is equal to mgh and mg h sub naught. So I'm establishing h is equal to 0 here, plus y. Now, I'm not doing minus y because y is a negative number down here. I have the peak at 0, 0, so this is a negative number. Same as we had before, so I have mgh sub naught plus mgy. I know that y is equal to negative ax squared because I'm making this a parabola just for the sake of an example. And so we now have a negative thrown in here when I make the substitution in for y. And so I set the force equal to 0, which is the negative du dx. Work it out, and this only occurs at x is equal to 0. So I have an equilibrium at the very peak. So again, I had my hill like this, and 0, 0 is right there. So I can have equilibrium. And I know it's unstable, but let's show it mathematically. So I have d squared u dx squared is equal to negative 2 mga. So taking the derivative, and we end up with, again, that's the first derivative right there. Take the second derivative, and it's less than 0. We're dealing with a local maximum, and which corresponds with an unstable equilibrium. Now let's go to a more complicated problem. I have 3 masses here, mass 1, mass 2, and mass 3 is in the middle. I'm assuming mass 1, mass 2 are fixed. In other words, they will not move, and there's a distance L between them, and I want to figure out where is the equilibrium in between. So I have this value of x. Now there are other ways of doing this, but I'm going to do it from the potential energy point of view. In general, the gravitational potential energy, assuming little g is unknown or not constant-ish, it's negative big G S A mass B over R. So in our particular case, the potential energy here, I have 3 objects. So I take the potential energy of these two, plug it in, potential energy of these two, just plug in, and the potential energy of these two, and I just add them together plus some constant. I haven't really established where potential energy is equal to 0, so I'm just throwing that constant in there. So I take the derivative with respect to x, and I end up with this. I know the force is equal to 0, and so I have this, And so then I establish that the force between mass 2 and mass 3 is equal to the force between mass 1 and mass 3. And direction's already been taken into account. And so we end up with m2 over L minus x squared equals m1 over x squared. Now it's a math problem, so I'm going to take the square root of both sides. It's a little bit simpler than cross multiplying and ending up with a quadratic. So take the square root of both sides. Now I cross multiplied and not dealing with a quadratic anymore. And the right-hand side, I go ahead and distribute. Then I get my x terms together, and I end up with a value of x is the square root of m1L over the square root of m1 plus m2. And this will tell me the equilibrium point. Is it stable or unstable? Now, if you're having difficulty imagining, so we have the two masses here. If I tap mass 3 slightly, will it keep going or will it come back? Well, because mass attracts and distance matters. So if I have these three masses here, if I tap this one slightly to the right, the pull from this one lessens, the pull from this one strengthens, so it should keep going. So it should be able to show that it is an unstable equilibrium. To find out, we do the second derivative. Well, we take the derivative of my first derivative, so we're taking a second derivative. This is my sort of my starting point. I'm taking the derivative of this, and I end up with this term right here. I know that big G, it's a constant. Mass 1, mass 3, and x are all positive numbers. L is a positive number. Mass 2 is a positive number. So since I have a negative in front of each of these terms, the whole thing is less than 0. We're dealing with a local maximum. It is unstable. So now let's take a slightly different problem. We're dealing with charges, and I know that the specifics of this are out of the scope of Physics 251, but the potential energy formula, I'll just give it to you. It's very similar to the gravitational potential energy, except there's no negative sign in front. So we have K sub E, which is known as the electrostatic constant. It is a constant. It is a positive number, times the charges over X plus, again, same thing. We do the potential energy of these two, then plus the potential energy of those two, plus the potential energy of those two. I am imagining all of them are positive. You can equally imagine them all negative, just they're all the same sign. So because they are like signs, they are being repelled. So Q3 is being repelled by Q1 and repelled by Q2. Take the first derivative, and it's the same math as we had before. The equilibrium point is the square root of Q1L divided by the square root of Q1 plus Q2. Is it stable or unstable? We do a second derivative. And again, just convince yourself that this actually is true. So we're taking the derivative of the first derivative with respect to x, and we get that. And eventually boils down to this. Q2 and Q3, Q1 and Q3, that are all positive numbers. Matter of fact, everything in here is positive. L is bigger than x, so that's positive. So we end up with something that's positive. Therefore, since my second derivative is positive, it is a local minimum. Therefore, it is a stable equilibrium. More conceptually, if I have Q3 and it's being repelled, so it's being pushed by Q2 this way and pushed by Q1 that way, if I nudge Q3 closer to Q2, the force from here becomes stronger than the force from here. And so since the repulsion is stronger, it will get pushed back. And it'll pass that point, and then if given the equilibrium point, if it moves closer to Q1, Q1 suddenly becomes a stronger repulsion and it'll push it back towards the center. A stable equilibrium. And there you have it.